Okay. Chat. There we go. Can everyone hear me? You can say something in the chat. I'm assuming that.
Yes,
no.
I can hear you.
You can hear me. Okay, good. All right, good. So we'll and you guys can see the slide there to the physical database design slide. Or am I sharing the screen? Now, yeah. Okay, now you can see it. All right. Okay, good. Yeah. You can see it now, right? People can confirm that. So I'm assuming everybody can see the slides. Yeah, good, good. Well, okay. I'm sick. I hope it's not the COVID. I just did the. I'm not sure how many people have done this, but it was terrible actually. We'll see. I'm gonna hand it in and see if I have the COVID, but I hope not. All right. Anyways, so let's just resume here, unless there's any questions. Are there any questions right now to start out with? People are slowly getting their projects approved, which is good. So I encourage people to do that. Recitation number 2 is going to get released quite shortly, actually. Should be early this afternoon. And then that will be, then we'll actually hold recitation exactly in 1 week, so on next Friday. And yeah, I think it should be pretty fun, a pretty fun recitation. All right, so let's just go on here, unless there are any questions. No. So this is what we covered last time, just to kind of refresh here. Mostly it was just about like how well, a single table, how its records are put on disk in blocks, and then how indexes are built on top of those blocks to allow for special access. So like, and these are the kind of the fundamental ways that you might access all of those records in a table via blocks. And the key-based access would be something where you're just putting in like an actual value, like a personal number or a city that a person lives in. Sequential processing is you're going through the whole set and you're calculating something or other, like the count or like the average salary or the average age or something. And then range queries are similar to the key-based access, but what it's doing is you're going to be focusing on a particular range. So say the personal numbers between a certain number and another number. All right. So those are the kind of things. And what we showed before then was just that this was just kind of some basic work talking about what indexing kind of means. But the key thing was these B+ trees. So this is the way things are done in databases now, B+ trees. So we went over the the basic ways in which B+ trees are. Okay, now this is important. This will be important for recitation, is to have some familiarity with these equations and to be able to kind of. I'm going to give you guys a paper example, and then I'm going to want you to kind of determine, well, what's the likely maximum height, or what is the maximum possible height? What's the minimum possible height of a particular B+ tree under a set of assumptions? All right. Then we covered a little bit of these bitmap indexes. And then finally, we talked a little bit about extensible hashing. Okay. So now let's just get to some maybe more practical thing. This is what you're going to be doing in recitation also. That is just, well, actually, how do you actually build these indexes inside of PostgreSQL? So you want to be able to actually bring this to actually put these things to use. So how do you do that? All right. So the way you do that is, of course, through SQL, through these SQL commands where you actually create indexes. All right, so the B plus tree is the default in PostgreSQL and in most databases. And let's see here. The thing is that when you declare primary keys, actually you're already building some indexes automatically. So primary keys always get indexes built for them. B plus tree indexes built for them, kind of as a default. But as you'll see, a lot of times to support certain access paths, you want to build your own indexes over different attributes. And these are usually going to be then, secondary indexes, which are going to be dense by definition. Hash indexes, you can build those. You'll see that you can build those in PostgreSQL, but they're not really widely used. There may be a special case in which you would do that. One thing also just to keep in mind, if you look at the PostgreSQL manual, you can also do stuff like you can do re-indexing. So after there's been a lot of updates to things, you can re-index them. And then another thing you can do is you can do clustering. So you can actually re-cluster on something other than the primary key potentially. So clustering means, again, that in the actual blocks that represent the table, like the sequence of blocks that represent the table, which in each block has records in it, you can basically have it so that's actually going to be sorted on something other than the primary key, right? Because it'll be sorted on the primary key as a default, but then you can go and you can actually change that. So, there are two other indexes that are worth talking about. Just referring to, we're going to cover these later in the course when we look at querying like no structures, querying text. And these are the generalized inverted index. These are basically indexes that go over text structures. The gin and the gist. So there's some interesting trade-offs between these two, and we'll cover that later in the course. So stay tuned for that later. All right, so let's see here. So the actual syntax in SQL or in PostgreSQL is to create an index. So if you want to create an index on the SN, so right here we have we want to create it on the SN, so that's a student name. So you're going to create index student name. So the ID here is the primary key, right? So it's already going to get a B plus. It's already going to get they call it a B tree, but they mean a B plus tree. B tree is a little bit older structure. So you want to say B plus tree, but what we see here then is that we see that we are creating the index SN student name on student. So you basically have the name of the table, and then you have the attributes. So in this case, there's only one of them that you're building the index over. Okay, so there you are. This is going to be a secondary dense index. It's going to have to be secondary because the primary is already taken with the ID, and it's going to, because it's secondary, it has to be dense. All right. So yeah, so there we are. If you then do a /D in PostgreSQL and get the information, you'll see that there's then going to be this this index with the name SN. And the reason why you want to have that the name still around, you could do this without having a name, but it's nice to have a name there, so then you can actually go and you can go and drop the index, right? So you can go and you can drop it, as you experiment. All right. So yeah. So all right. Okay. So another thing you can do also is that indexes can be partial. They can be specified on a condition. So it's usually the condition. You can't have subqueries in the condition. The condition is something like, so you might actually see this. There'll be an example of this actually where I'm gonna ask for you guys to do this for one of the questions in the recitation. So you'll see that this is something where it's like, if you don't want to build the index maybe for the whole data set because it would be prohibitive. Sometimes these indexes can be very expensive and they can take a long time to build. Okay, so, and you'll see that later in recitation, that when you do a create index, it can take now forever. Yeah, I mean, practically forever if you're not careful. All right. But sometimes what you'll do is just over a certain part of the data, you want to build the index. So here's an example here where we're going to create the, basically an index on the department name where the department name is comp sci or electrical engineering. So what this means, it means that if we're scanning for students and we want to scan for those departments, we say, well, the department equals comp sci, we'll get really fast access to those students. Okay, it'll really speed things up. But if we say biology, it won't, because it won't be hitting that part of the index won't be touched. All right, so Yeah, so create an index where the total credits are greater than 50. So we're going to create an index on total credit where the total credit is greater than 50. So these are students that have gone further in their studies. The index can't be, it has to be, so these conditions here are not really dependent on the database state. So for instance, these conditions won't go true or false based on the database state. They will for a particular tuple, but the thing is they won't be kind of impacted. The thing is that if you had something like where you said some other kind of condition that could be altered by adding other stuff to the database, like you would have in a general subquery, that would invalidate, or that would make it so that it would be very hard to maintain the index. So these conditions inside building the index are fairly they need to remain fairly simple. All right. You can also do a transformation. So you can, basically what you can do is you can, for the different tuples, you can do a transformation function on the values and have that stored in the index as a search key. So this is a kind of an example. You'll see this happen a fair bit. That is what you do is you basically will do the lower name. So you're going to create a index on lower name that applied or transformed on the data name. And then if you have queries, only a query where you're calling for lower name will actually fit over that index. All right. So, but there'll be cases where you want to do this. All right. So then there's an issue of the having multiple attributes. So I mean, in this university example, it doesn't. I mean, this university example is so small, anyways. It's not going to make a difference. You know. But in the example recitation, this will actually make it. We'll actually explore some of this. So what this right here is doing is creating index where it's like the name is. So if you think about this kind of like how it's being organized here, is that you have the name of the student and then the department name. All right. Now, what that means is it means that it'll do it from left to right. So the first thing it's going to do is index on name. All right. And then it's going to index on department name. All right. So what this means is it means at the very top of the index. So the index is like, it's still, basically what's going to happen is that at the very top levels of the index, it's going to be doing conditions on the name value. And then when it gets to a certain point where the name is already decided, then it's going to do conditions. It's going to kind of branch out on department at that point. So if you think about it, this actually doesn't make much sense. This is kind of a little bit silly as an index in a way, because if I say something, now it would be, if I said something like John Smith in computer science, then, well, yeah, I mean, what it's going to do is it's going to then basically, it's going to find Smith, and let's say there's two John Smiths, one's computer science, one's in chemistry. So it'll go down, and then at the very bottom there, it'll then determine that it's computer science. But if you do it the opposite direction, so first you're gonna build the index based on department name, and then you're gonna do the name after that. So if you do it that way, so you build it on department name and then name, then it kind of makes a little bit more sense, because you're going to get, I mean, you're going to wind up. So the question is this. I mean, this is kind of an empirical question. Would PostgreSQL be smart enough that if I built this, instead of building name department name here, I said department name, and then I say give me all the students in computer science, would it take advantage of that multi-attribute index? That's the question. Okay, so well, we can look into see if it would do that. If it would do that, then it makes sense to actually have department name then name. All right. Because then you're getting double use out of it. But we'll check to see if that actually happens in PostgreSQL. All right. This index might be useful for finding tuples matching the value for attribute name, but it's not. Yeah, that's right. Okay. All right. So here's this thing I was talking about before about reclustering or clustering tables in PostgreSQL. So they're clustered in the order of the primary key by definition. You know, that's the default. But this might be changed by using the cluster directive. So you can say create an index student name, and then now we can cluster on name if we say cluster student using that index. All right. So you build an index and then you use that to cluster. All right. So oops. So this can potentially give you pretty big speed ups in a big database. Right. So you can only cluster on one, using one index, of course, because there's only going to be one. You can only cluster on one. There's only one way to cluster something. I mean, it's once it's clustered as its physical order on disk. All right. So as things change, so as your as you make updates, of course, it's you especially you make a lot of updates, deletions, insertions, updates. Then it'll start drifting out of its the clustering will kind of get worse and worse because it's going to have to can't move things around, right, as it's as it's inserting things. So it kind of will put things on the end, and it'll use a little bit of pointer chasing to kind of have extra overfill blocks and stuff like that. So you want to kind of recluster it if you want to put those blocks, align those blocks again in order. So that you do that with the cluster statement. Right? So you would periodically do this. Likewise, the index itself is going to be changing a lot. So the index itself is going to undergo a lot of alterations. And what you might want to do is you might want to do this re-indexing. So you rebuild the index. Okay, so this is the kind of thing. This is kind of one of those 2 o'clock at night kind of operations where you rebuild the index. Right. You can also get in there, and you can also do stuff like you can start messing with the fill factor. So in other words, I mean, these are more, what Postgres is using is a little more of a generalization of B+ tree. So it's not that exact half full condition that we have. That was more just kind of the initial B+ tree, but they are altered. So you you can go in and you can change the fill factor on the index when you build it. And this might actually have this might make a lot of sense based on the mix of updates. Again, remember the big cost with B+ trees is if you're gonna either shrink or you're gonna grow the height of the B+ tree. That's an expensive operation. So sometimes you'll kind of trick around with the fill factor to kind of try to avoid that. All right. So if you get close to you want to keep things kind of a low fill factor so that you can always make a lot of inserts. So if you're insert heavy database, you would do that, and then maybe when you do the reindexing, you kind of tinker with the fill factor so that you can knock it up to the next height early in the morning, and then over the course of the day, it won't undergo any kind of expensive, on the fly growing of the height of the B+ tree. All right. Yeah, so you can do hash. It's still in there, but it's not. I don't know. I mean, the question is it how robust have they made it? Because I don't think it gets used that often. And then this Genius, we'll put that off for later. Okay, so choosing and evaluating indices in PostgreSQL. Well, how does one decide to which indices? So the short answer is that, I mean, so in other words, what indices should I build? What shouldn't I build? There's a trade-off there, of course, because I mean, if you build too many indices, then or indexes, I prefer just basically indexes, make it more regular. If you build too many of them, then every time then what happens? They have to be maintained when you do the updates. So that's something to always kind of consider. Try to don't build too many, right? Especially if you're going to have a lot of updates. So the idea then is that it takes a fair bit of knowledge. I mean, you have to kind of play around with this and kind of have like the parameters, like what are what you have to do a lot of times. Also, you have to look and see how the PostgreSQL is actually planning and executing your queries, and we'll come to that in this momentarily here. So you do that, but basically it's kind of experimental. It's like empirical. You kind of play around with it. I mean, I think the thing is to remember also is that one of the assumptions of databases that may or may not be true. It's becoming less and less necessary, but the general assumption of databases has always been that the contents of the database, the contents of the index, even the index. They can't fit in main memory, so that you're always dealing with kind of you're always going to be dealing with like moving things from it. Even under the period of a query, you might be forced to move things from and to Baka from main memory. So from and to and from main memory. That's kind of an assumption, but then the thing is that a lot of times in practice now that's not really happening because memories are so big. So anyways, it's an art. So okay, so let's go now. If there are any questions on this, speak them now. Oh, good. I believe it does. Okay, so the question was, does clustering also handle defragmentation? I believe it does kind of implicitly. So this is, again, one of those things where you try to figure it out empirically. So when you recluster, it is going to kind of, well, let's put it this way. When you recluster, it's going to basically bring everything in. It's going to kind of write it out to what it thinks are sequential blocks on a disk. The disk controller and all that other stuff, especially if you're doing like an open source system where you have the operating system on one hand that's managing aspects of the disk, and you have the database which is managing other aspects. The question is it really going to do a full defragmentation of the disk? And I don't know, maybe not. But the thing is, it might be that if you really want to make sure, what you would do, the way to test it would be this: is that you would say that, well, I have a large database that's undergone a lot of updates, and so, all right. So presumably now the file itself, the data file that corresponds to a table, is in a state which it should be reclustered. All right. So you recluster and you check the performance. Oh yeah, well, it got a little bit better. You do a sequential scan and you see that it select count star from the table, and you see that it actually is improved because now everything's clustered, and you're not doing a whole bunch of disk seeks when you're doing it. Okay, when you're wrapping in, and then you say, well, okay, and then you go to the operating system side. So you measure how much that was, and then you go to the operating system side, and then you say, let's defragment the hard drive. Okay, that goes on. All right, then maybe you want to come back and then recluster again. Or it's hard to say, but the thing is, it might change things. It's a tricky question. I think it's an empirical question. So what I mean by that is that I think that you just try it to see it, because I could see both. I could see how it would make a difference. So in other words, I can see how they're distinct. How defragmentation is not the same as clustering. Okay. Are there any other questions? All right. So. Alrighty, so let me see here. I'll go over here, take this puppy down, and I'll go over here. And now we're going to go into, so now we're going to assume that we have all these, we have these indexes that are potentially built, and now we're going to basically start talking about, well, how is the actual, is the only drawback that you have to maintain it? Oh, the only drawback of building indexes? I'm assuming that's what you're asking. I assume the question that's being asked here is the only drawback to building indexes is that you have to maintain them. Well, they're also big sometimes. So, I'm sorry, I should be looking this way. So they can take up space, but that's just usually just space on disk. But then it becomes space in memory. But it depends on the nature. So. No, so the answer is no, because there's also the issue of space. How much space does the index take up? And then there's also a question that it's a very subtle kind of point, but I'm not really sure of how smart PostgreSQL is. But if you build too many indexes, then you boggle the query optimizer, because it then has to consider all the different choices. Right? So if you can build a combinatorial number of indexes, right? If you have n attributes, you have n attributes in a relation, then essentially you have 2 to the n. No, it's worse than that. It's probably n plus 1 factorial or something, because you can pick them. The sequence matters, the direction matters. So it's a big number of potential indexes. So a naive thing to do would be just build them all. And then the thing is that then, of course, there's a combinatorial number of indexes that the poor optimizer has to pick from, and that boggles it. So that could potentially cause it to for you to have really bad query performance because of that. Potentially. I'm not sure. It probably just cuts off, though. I mean, that'd be an interesting thing to try with PostgreSQL to see how smart it was. So if I build just all these combinations of indexes, does it really slow down the query planning? I think in early databases that would happen. But they probably have a cutoff where they just cut off deliberation and say, no, we're not going to look at any more combinations. All right. Please on. All right, query processing. Let's see, got to keep an eye on the time here. All right. Query processing. Okay, so, all right, so in comes an SQL. So we have, let's say we have a bunch of indexes and we have a database, it's all kind of organized, all the files. excuse me, all the tables have their own separate data file, as it were, which has all these blocks and stuff like that. But anyways, in comes our SQL. And well, how does this work? So if you look at the bottom here, if you look at this bottom kind of architectural diagram, the SQL comes in just a straight SQL, and it's first of all, it's it goes through this. We'll talk about this in a second, but basically this this set of processes here, what it does is it will take the SQL and it will turn it into this algebraic representation, which is basically the extended relational algebra. Right, so it's going to turn it. So if you recall from the database 101 class, is that SQL is technically a mix between relational algebra and tuple calculus. So thus, it has aspects which are declarative, like exists. That's a declarative construct. Relational algebra, though, is purely procedural. So relational algebra, you can plug it in and you can execute it. I mean, it's just there's no it's directly something that you can directly execute over relations. Okay, so the first thing that happens is that you turn the SQL into this extended relational algebra, and then since there are so many equivalent extended relational algebra expressions that do the same exact thing, then what you want to do is you want to have the query optimizer kind of search around and kind of modify and test different combinations, looking for one that it thinks, based on its predictions, which will execute the quickest. Right. So once it decides that, once it's finished with the planning, the planning is all going to be happening in main memory, looking at like statistics and kind of and doing transformations on the extended entity relationship tree. So it's pretty quick. I mean, in the sense that it's like, it pays to kind of think a little bit before you then go off and do the execution. Because once you do the execution, then you're talking about bringing in large amounts of data from disk. And even if it's in main memory, you're talking about, looking over, doing scans of large amounts of memory. So it pays to kind of think a little bit, to deliberate before you act. And that's what this query optimizer is doing. Okay, so if we look at these in a little bit more detail, so what's going on in this kind of scanning, parsing, and view resolution? All right, so the first thing you have is you have a lexer. So the lexer, what it does is it scans through, it goes through the, first of all, it tokenizes, right? So it breaks the input into a set of tokens. And then it basically figures out, well, which of those, some of those tokens are going to be database tables, some of those tokens are going to be SQL keywords, some of those tokens are going to be literals, like literal values, like 455 or something, right? Or any quote something, blah blah blah, end quote. Those are going to, so basically it's going to go through and it's going to do that. So that's kind of normal that you expect that. So then it's going, once it breaks it up into a set of tokens, then it's going to parse them. And SQL is actually, it's got to like keep this in mind. Don't name your attributes things like order or select. Try doing that. PostgreSQL won't let you. I mean, it'll freak out at create table time. So if you try to create an attribute called order, it doesn't like it. All right. So yeah. So I mean, just stay away from the SQL keywords when you're defining table names and attribute names. All right. I mean, it's a hard lesson that people have to learn. I mean, there's been a lot of. I'm sure there's been a lot of wasted. Yeah. I mean, it's something that I shouldn't laugh. I know it's but it's just the way it is. Right. So anyways, so it breaks it into these tokens, and then it does a parser. Okay. So then that builds a parse tree. SQL parse tree. These are real. This is talk about grubby code. This is, I'm sure, is the grubby. Some of the grubbiest code inside of PostgreSQL is this parser. And then, of course, it parses it, builds up that, and then what it does is it will plug in the definition of the views, which is the way it's typically done, which is kind of elegant in its way. That is that if I have some view that's kind of that's basically advanced student or something, somebody in the honors college, it'll go in and it'll, like, if I'm doing a query over advanced student, it'll go in and it'll plug in that definition just kind of at the SQL level. So all that comes out then is just going to be one big SQL. That's view resolution, and then it's going to translate that big parsed expression, the parse tree of that thing. It's going to translate that into the extended relational algebra. All right, so this is actually, I mean, this is a tedious task. Actually, it's not completely non-trivial, but it's just, you just have to kind of keep your definition straight. But things like exists and stuff like that, kind of, you know, when they translate out to a relational algebra, you've got to like there's a fair bit of bookkeeping. It's very tedious, but anyways, it has to happen because you have to generate this algebraic expression. All right, so the algebraic expression comes in, and then you have the query optimizer. So the query optimizer, essentially there's two distinct processes that it does. So it's going to basically try to kind of look at generating. What time is it? It's going to try to look at generating, you know, a fair number of alternatives, and then it's going to then annotate those. Then it's going to have to look at annotating those alternatives, and that basically has to do with from this expression in relational algebra. You basically have to determine which indexes you're going to use and what algorithms are you going to use. So there's a lot of times there'll be a choice there as to which you should use, and we'll show some of these algorithms later or soon in this lecture here. But in the end, what's coming out of this is an execution plan, or what comes out is a set of execution plans, and then the optimizer just has to make it based on its predictions. It has to basically just pick one. Right, so it's only going to evaluate. It's only going to actually evaluate one, right? And then once that happens, then we're going to go to this cogeneration and evaluation. So the cogeneration and evaluation, we'll talk about this in a bit. So basically, it's just kind of going to carry out the relational algebra. It's going to basically carry out those algorithms. The only thing to keep in mind a little bit with that is, I mean, there's a lot of implementation details, of course, but yeah, we'll cover that at the end of this lecture. All right, so the algebraic representation that comes in. So it's going to be a rooted operator tree where the leaves are relations, the input relations. The evaluation is going to be bottom up, and the root finally corresponds to the final result. So if we look at this example, so give me the name, excuse me, the names of the instructors that are in a department that's in Meet Husid. Okay. This would have the following tree representation. So this could be the following tree representation where you're basically going to have department come in here. You're going to do a select on Meet Husid. Then you're going to do a natural join with instructor, right? So the instructor has a department name, and that's who's going to. And then once that comes up here, then you're going to do projection, and the name from the instructor is going to project out. Okay, so that's you know, pretty straightforward. So this is kind of how these things represent. That's how the algebraic tree is represented, and how it you know, what the meaning is of it procedurally. All right, so the database, you're expected to write semantically correct queries, but not optimize them. So the SQL then then the optimizer will be able to figure out what a good actual execution plan is. Transformation is using equivalence rules. You're using equivalence rules in the one second. Gotta make sure I can bring this up. Using equivalence rules, and I'll show them right now. Just rotate this. These are the ones that we consider in this class. There's actually a lot more of them. There's an infinite number of equivalence rules. Rotate. Yeah, there we are. Okay, I'll just stage this ready to show this to you guys. Huh. That's a little bit of a bummer. There we are. Then you try to use statistics, so like this catalog statistics information, to estimate what are the sizes of the relations going to be as you execute them, and then you're going to pick a choice of using the size information and plus also what indexes you have. You're going to pick an optimal plan of execution, or one that's rather good. Okay, so let's get a specific case here. So here comes the SQL select name. This is exactly the example that we were looking from before. So the parser itself might produce something like this, where you have department and instructor being natural joined here, and then the select is happening on top of that. All right. So this one here, this right here, when you do this join here, it could potentially be fairly big. And then that's going to then get pushed through, and then you're going to do the selection of meet Houston on top of that. Now, if you look at this other one here, where you're actually pushed the selection down past the natural join, this one is better. The one on the right here is better because it's as a potential. I mean, if you have a large number of departments, this and then large number of buildings that departments can be in, they're not going to some other building in the campus is not going to. Department in some other building is not going to make it past this point here. So this has potential to be quite small when you're going to be doing the join. All right. And generally speaking, when you do joins, you want to make sure you want to get the sizes of what you're joining as small as possible, because that's one of those. That's a very expensive operation. It has a potential to kind of blow things up, especially if it's just a straight Cartesian product. All right. Notice here that having, this is bad. This one here is bad, right? But you could make it even worse if this was a Cartesian product, and then above that Cartesian product, you had a select, right? So the fact is that when you have Cartesian products, there's a reason why it's extended relational algebra, because you have these kind of things like Cartesian products for outer joins. When those are plugged into one of these trees, then it's going to basically be an instruction to the algorithm to do the natural join as it's processing the tuples. It's not going to do a Cartesian product and then do a select on top of that with the results coming out. No, it's going to be inbuilt. The natural join is going to be inbuilt in the actual algorithm that joins these tables. All right, so that's something that gets taken advantage of when you're doing optimization. So, see if there's any questions. All right, so if we look here, if we look at basically this case right here, where we have this. You want to transform this into that to make it more efficient. So one of the general heuristics is that you want to push selects down as far as possible. But anyways, what allows us to change this to that and not worry that we're going to lose something in the process? Well, that is where these equivalence rules come in. One second. So these are the equivalence rules that. I have a copy of this on Cambro for you guys. These are all just kind of these are all axioms, so they always hold. These are just these are equivalent, right? It's kind of a little bit informal because there's some aspects that kind of that just need to be described linguistically to kind of elaborate the cases, but. Basically, these are the ones that you can consider to be kind of a fairly complete set of equivalence rules. So for instance, in here, like you have commutativity between selects, so it doesn't matter the order in which you do selects; it's always going to be equivalent. All right. Given that, think about it. Then, if you can commute, just a minute, if you can commute selects, then is it better to basically say something like, like, give me all the if I have a select that says something like that will give me all the people, give me the instructors at the computer science department, or give me the instructors who have exactly a salary of exactly 70,000 or something. Which one would be better to apply first? Computer science is going to generate a set. There's going to be a lot of instructors that are going to make it through computer science. The salary 70,000, well, we don't know, but let's say that it's 70,001, and we're looking for one particular person with 70,001. That's going to be fairly high. That's going to be pretty selective, highly selective. I guess a better example would just be like, it's not. Well, let's just stick with the salary example. 70,001. There's probably like 4 people across the whole university that have that exact salary. Whereas in computer science department, we have, let's say, 60 people who are in the computer science department. Therefore, the condition on salary is more discriminative, or it results in a smaller answer set. So actually, that's the one you want to apply first, because it whittles it down very quickly to something small. And then you can check, well, we got these 4 people who have the salary. Then we can see who's in computer science. Versus we have the computer science. Now we got to check everybody for the salary. Right? Now you might say, well, without indexes, isn't kind of okay. Without indexes, it doesn't make that much of a difference. But with indexes, we'll see that it would make quite a bit of difference there if we had an index exactly on salary. Yeah, but anyways, if you don't have indexes at all, then you just kind of you run them together, because then you just want to do one scan of the full table and check, okay, well, both conditions, salary, exactly this, and department computer science, because you're going to be going through all the tuples anyways. But if you're going to use indexes, then it would make a difference. All right. So anyways, that's just an example there where you may find that there's some kind of potential optimization that can happen just around this particular equivalence. Some of the other ones get a little more complicated, but we see here that there's yeah, I mean, you can read through this. We're going to actually touch a couple of them in a sec. All right, so if we say something like this, we say, well, why can we do this? Why can we move this one here to that? Well, the reason is because, well, there's this one condition that's Rule 7 here, Rule 7, and what that basically says, what Rule 7 says, and it uses language to describe it. It's not, making it completely over formal. But what it says is basically this: if you have a selection that only applies, that is only over attributes on one side of a natural join, then you can just basically distribute those conditions to that side where they're relevant in the natural join. So that basically means when you push it down, I don't want to do that. You can push it down to this side here, because only E1 actually has the theta condition E0. So when I say building equals that, there's only a building. This condition only applies to department, and this equivalence here lets me push it through the Cartesian product, or the natural join. All right. If you look at it a little bit closer here, so that allows us to do that, and now we're getting something more efficient. If you look at the one sec. Yeah, so if you look at this right here, if you look at this this case here, where maybe we want to put this this instructor relation that's coming back here, we want to put this thing on a diet. We want to slim it down. Because maybe there's a lot of attributes, right? So you want to make things small. So what we want to do is only name is going to be used, and only department name is going to be used to kind of do the natural join. So why don't we put this thing on a diet and just kind of slim it down so that it just has name and department? So that intuitively you can say, yeah, that would make sense. As a human being, you know that would be the case. So, but it takes an application. I won't go through it because it's a little bit tedious, but it goes through the application of these 3, 5, and 8b rules. So you would use these rules to show that it actually is equivalent to do that. All right. So the computer would require a little bit of search to do that. And so this kind of brings up an issue that, well, I'll touch on it, definitely touch on it. But before I forget to remind to say it, I'll just say it again. This optimization stuff, the optimization. That using these kind of rules here to search out what's the optimal query execution plan. It's a bit optimistic. Let's put it that way. So what happens in the quote real world is that maybe there's somebody who's like struggling with some giant database table, and they need to do this, but the optimizer somehow doesn't see it. So if you write your SQL, a lot of times what will happen is you'll actually go and you'll just kind of look and see how the thing's actually doing. You'll say, the optimizer doesn't see things so well. So I have to go into my SQL and complicate my SQL so that the optimizer, once it parses it, it will say, oh, okay, it'll allow that to go through. So sometimes you're the actual optimizer, you, the programmer who's doing SQL. Sometimes you actually have to write the SQL and not, you can't rely on these equivalence axioms covering all possible transformations and finding the correct optimization. So a lot of times they like to say that, oh, it's going to do it for you, but a lot of times in practice it doesn't. You have to kind of do it yourself. This might be a particular case. I'm not sure if PostgreSQL is good enough to do this. All right. Yeah, this is just showing that using the equivalence rules. Yeah, so it's fairly involved to show how you can actually go and basically apply the insight of putting extra projections here to make things smaller. Yeah. Now this is an example exactly of that. So if you look at this right here, and we'll come to this later on in this lecture, and you can verify this in PostgreSQL, but it doesn't get this. So in fact, if you look at the equivalence rules we have, it doesn't even cover this because it doesn't deal with like taking intersection and then kind of when there's uniform selects, combining those in an and instead of doing intersection. So it's not going to be able to see that this is equivalent to that. All right, it's not going to be able to see that. So intersections and except like minus and union, it doesn't. A lot of times, these optimizers won't be able to kind of repackage those queries into something that just is doing a single pass over the table. So a lot of times this will be very problematic, actually. You would rather do it this way. So if you say the name in an instructor where the name is computer science and the salary is greater than 70,000, that is equivalent, of course, to getting the people in computer science, getting the people with 70,000 and then intersecting the set. Those are equivalent. But this one, of course, would be, you can already look at it and you can say this is going to be more efficient because this is going to require you to pass through the instructor table, do a scan on that. If there's not an index on that, you have to scan that, you have to scan that. So you're doing 2 scans and then you're combining them. So you'd rather do it this way where you only have 1 scan and you're just kind of checking the conditions. So it's not, but again, if you put this in, it's not going to be able to find that. It won't do it. So the lesson is put this in. Try not to I mean, this is something, intersects and set minus is, set minus is particularly bad because set minus actually blocks getting answers back. So you don't have this, I'll get to that a bit later. So yeah. Let's see, what are we looking for? Time here. Oh, let me see. I think that maybe this would be good timing here. Okay. Yeah, good. Let me just finish with this this slide here, and then we'll take a 10-minute break. Yeah, so it looks around for an equivalent. How does it choose which plan to execute? So there's a huge number of equivalent operator expressions, of course, and we talked about that. So dynamic programming can be useful. I think that there's a little bit, I remember seeing at one point that there was a genetic algorithm that PostgreSQL was using, or you could turn it on to use it. I'm not really sure. But it's an optimization problem. So the size of the relation, so statistics on the size of the relation, and then also even like the cardinality of the different constants, or like getting some idea about what's the number of constants for a particular column will be useful. Then heuristic. So the very common heuristic in natural is to move operations which reduce the size down deep into the tree before you do stuff like joins, which are things that increase size. Yeah. So anyways, what we're going to cover now then, when we come back from break, what we're going to cover is it just occurred to me, I'm pretty sure I'm recording. If I'm not recording, I'll be angry, very angry at myself. What we're going to show is we're going to show basically those. Now we're going to take like the stuff we're talking about, indexing, the indexes, and we're going to move them into these basic operations, these basic operators of relational algebra, and we're going to see how we can plug in and get use out of those indexes. Right. So we're going to do that, and then we're going to finish up talking a little bit about execution. And maybe we'll finish early today. We'll see. Okay, so let's see here. Now, when we come back, we're going to talk about each of these relational algebras.
Mr. Minuk?
Oh, yeah.
I asked a question regarding the SQL instruction in page 14. I asked if that symbol that looks like U, is it a space in SQL?
You mean the union?
union, but how would you write that symbol on the keyboard?
Oh, you just type out union. Let's see. What did I have here in terms of? Was there any particular? Oh, you mean here?
Yes, sir. It's where you have comp dot, then you have that symbol of union, and side dot. How do you write that on SQL?
I don't know what slide you're referring to, but in general, what you want to do, I mean, there's in SQL, you basically have you have intersect, and then you have set difference, which is except. That's the way it is, and then you have union, which is union. You just type out UNION.
You just type it as a word.
Yep, union.
Okay.
Yeah, it's a keyword in SQL.
Okay, no worries then.
So yeah. So good question. So, are there any other questions here? Let's see. Yeah, the problem is I'm not I think I have an older version of Zoom, so when somebody sends a message, it doesn't automatically scroll it, so it sits there and it yeah. Maybe if I make the whole thing bigger so that I can. Oh, good. So that removes the scroll bar. Yeah, very good. Okay. All right. So let's take a 10-minute break. Let's be back at 15 after, I guess. Yes, it'll be 15 after, and yeah, and then we'll resume. I'll pause the record. Huh. That's weird. All right. Okay, now I think we can resume again. Right. Excuse me. Ugh. Let's see. I assume you guys can see this, right? Just send me put a message. Okay, good. All right. I really hope this isn't the COVID. If it is, I mean, I'll try to. Yeah, we'll see. I mean, I guess the chances are pretty low because, yeah, I mean, so few people had it in room now, so I'm assuming it's just cold. Right. Okay. So, it's important to develop cost models. So basically, what this cost models means, a cost model is something that lets you do prediction about how expensive something's going to be. Because as you're doing the optimization, you're going to kind of deliberate over potentially large number of plans, and you want to kind of estimate or model how much they're going to cost. So what you do is as you might alter the tree quite a bit, and then you will have different algorithms you might be able to attach to it, and different maybe you use the index, maybe you don't use an index, maybe you use this index but not that index. So there'll be lots of you want to get some kind of estimation, and therefore you have to have a model of how these things, how much they cost, given indexes potentially. So we're going to just basically do all the kind of basic operations in relational algebra. So extended relational algebra, selection, projection, removal of duplicates, join. Join is the big one, and then the set operators and operations, and then the aggregation. All right, so basically some of the basic models of cost are this, is that, well, you just have to have these constants kind of worked out. So what is the average seek time plus rotation latencies? What's the average time to access one block of data that's on disk? All right, so just, you have to go out, you have to seek it. I mean, so that basically is going to be the seek time plus rotational latency. So moving the read head and then waiting for the thing to spin around under have the sector under the head. Once you find that, once you have the block, so once you actually have it under the head, how long does it take to transfer one block of data from secondary to primary storage? So how long does it take to load it into memory, right? So if you have an operation, so if we have an operation that requires n sub s seeks, so the s there is for seeks, to transfer n sub b, so that's the number of blocks. This will require a total time then of, these are constants here, the seek time plus the transfer time. So let's just think this thing through here, because this will be important. What if I just wanted to go to a particular, for sequential processing, I just wanted to go to a particular record, and then I wanted to get everything after that. So I wanted everybody with a name or everybody with a persona number greater than a certain value. Let's say the index is in memory. Well, in that case, it would only take one seek to actually get to that first block. And if all the blocks are contiguous, so they're all kind of lined up on disk, then all it would be then is this one seek. So basically, n sub s would be 1. So we would just have the time for one seek. That's 1 times the seek. And then let's say we were going to transfer a million blocks. Then it would basically be the transfer time times the number of blocks. So that would be kind of a really optimistic case, right? But then let's think of a really worst case scenario. Really worst case. That is that every block is on a different part of the disk and requires a new seek. And we have 1 million blocks. That means we're going to have 1 million seeks plus 1 million block transfers. That's going to be really prohibitive. All right. So that's what we have to kind of consider. You have to consider that's kind of the dynamics of what an access looks like and how much it costs. All right. So I hope that's clear. Yeah, so the relationship between the number of seeks and the number of blocks is always going to depend on how they're arranged on the disk. Is it random or is it sequential? Sequential neighbors are much better, as you can see. Far fewer seeks. All right, so this right here is kind of, this is a lot of text, but let's just talk about what this means. All right, so this is to actually access the index. So we have this B plus tree index. So the cost of accessing the index, let's say that it's a path from the root to the leaf, where the blocks, so as you recall, the internal nodes in a B plus tree are blocks. So if they're in already, the blocks are already loaded, the index is already loaded into memory, is just negligible. We're just saying it's completely negligible. But then the number of seconds, the number in secondary storage then will cost 1 seek plus 1 block transfer for each node, for each internal vertice that is not in main memory. All right. So generally speaking, what this means, it means that you can kind of assume, and I think we will assume in most of our cases here, that the index is completely inside of memory, and thus it's just going to be a negligible amount to access the index. Now, in really, really big databases, that's not true. You need to bring in blocks from the index as well, because the index is so big, you don't want to have it just all sitting in main memory. All right. So now let's look at some relational algebra. So selection is all right. Sorry. All right, so selection is where we're actually going to be applying conditions. All right, so the simple case is that we have a select where we just have an attribute equal to a value, or we have an attribute not equal to a value. That's inequality on a single attribute. And then we have simple ranges, and then we have compound cases where we're doing ands or ors, or we're doing negation. So we kind of are going to consider all these at once here. So let's just consider a very simple select without index support. So this might be something like, let's say we have not built any indexes on name, and we have students, and I say, give me the students with the name John, with the, well, first name is John and last name Smith. All right. So what it's going to do is just going to do a linear search. So the number of blocks it's going to go through all of them. So basically the number of blocks is going to equal that. So that and number of blocks constant, or not constant, but parameter is just going to be the number of blocks in the relation. And then it's going to basically be that we're just going to do a table scan. We're going through and doing a table scan. We're going to go through every tuple in the table looking for John and Smith, because we have no indexes to help us. All right. So in this case here, if everything's contiguous, then basically we're only going to have one seek, but then we're going to have however many blocks there are in the file for transfer, right? Yeah. So that's not guaranteed to hold, but what it's going to do, if it decides it has to do a table scan, it's going to do it it's going to scan on the clustering. It's going to basically scan in cluster order. So it's going to take the primary key and it's going to scan on that. That's what it's going to do. So if if things are well set up, then it won't be that bad. I mean, but you still have to kind of grind through every single tuple on the table. All right, that's without index support. All right, now let's take a different case. Let's say we're that we've actually indexed. Okay, let's say that we're looking for the person with Pershon number, one particular Pershon number. And if there were no primary keys, then we would have to do a table scan. But if there was a primary key on Pershon number, then we have a single value that we're doing a search on, right? And we have an index built up for it, a B+ index built up for it. So this is the best possible case. So what it's going to do then is it's going to basically be, however many seeks and transfers for however many of the vertices of the index that were not in main memory, because you have to get those as you're going down, searching down that particular value for Pershon number. However many that is, plus 1, because you'll find it right then and there. When you finally get to the point where you're going to point out to the actual block inside the file, inside the relation, then you'll just find it immediately. Right? So that's the best possible case. Primary key on a primary B+ C on a non-key entry. So that what this is something where let's potentially say that what we're going to do is we're going to cluster the student table by name. All right. So the name is not the primary. Let's see here. Primary B+ tree on a non-key. So if we're gonna cluster on name, the name is not a key, because we could have 2 John Smiths. All right, but it is clustered on that, and we have a primary B+ tree on it. Then all it comes down to is basically, well, it's a potential that we're going to have whatever number of blocks that the name is going to span over. So maybe if John Smith there's so many John Smiths that they're occupying more than one block, then we'd have to kind of get 2 blocks instead. Or if there's like 7 blocks of John Smiths, God only knows how big. It depends on how big the university is. To have 7 blocks of John Smith would be a big university. All right. Okay, now we talk about secondary indexes. So now let's say that we have indexed on, we are indexed on Pershon number, but then we also built a secondary index on name, right? And then we're going to look for John Smith. So basically what it's going to do, since there's going to be a kind of a bucket file that's going to wind up having all the, we're going to build like an index over these the leaves in our index are actually just going to be these bucket files that have pointers out to the actual location in the true file, or that have potentially just have the key. They have the Pershon number there at that key. But let's just say there's a pointer out. Then in that case, it's just going to basically be we're going to add 2 to the number of blocks that have to be brought, that they have to be accessed. All right, so it's so we have all the index blocks that that needed to be brought into main memory that were not already there, and then plus 2, because then we have to get the bucket block, and then we have to get the actual block where the John Smith is. All right. So so these are all. But this is what this is showing here. Just kind of between the lines here, is it's showing that indexes really are helping. All right. So primary B plus tree index, simple range search. Okay. So on range searches, then what it basically does is you find the first element in the range, because it's going to be, in this case, it's like the Peugeot numbers between this Peugeot number and that Peugeot number. It'll find the lower one, and then all it will do is just kind of race along doing transfers and following the pointers in the file for these block pointers, these pointers in the blocks of the file, the data file, which basically say what's the next block in the clustered, sorted on the cluster, which is a primary key here. So all it does basically then is it says, okay, sure, we have to grab the these are still these expressions here are still including they're still including there's a potential here. Most of the time, let's just assume these are going to be 0 because we don't have any we have the index fully in memory. Basically, what's going to be is you're going to have to do a seek just to kind of get the first one, and then you're basically just from then on for the number of records you're going to do just data transfer. And this is the best case if everything is kind of stored contiguously. All right, so that would be nice. Secondary B plus tree, simple range. Okay, so here's actually where we could have some problems. Oops. So if you have a secondary, this is the issue. So a secondary one, let's take name. We have a secondary index on name, and then we're going to basically want to get all the names that all the names that start with last name starts with S and then goes to T. So Smith, all the we're going to get a giant range of names, but the relation itself is clustered on a Peugeot number. So what this means then is it means that basically we're going to be doing a lot of seeks, because we're going to go down, we're going to use a secondary index to find a whole list of different essentially we're going to find a whole list of blocks where inside that block there is somebody with a name that ends with S or starts with S. What it's going to do then is, John Smith, and then the first John Smith, and the second John Smith. The first John Smith is got a Peugeot number completely different than the second John Smith. So now we have to hop. We're basically going to hop somewhere in the file to the next one. So that's going to require a seek. And the worst case here is that we're going to basically have that we're going to have to do seeks for every single block in that search. So that could wind up being a problem. All right. Okay. So what this is actually showing that if the seek time could actually be eliminated or really reduced. So the seek times, there's still transfer times, and there's still some kind of cost associated with something or other, but if the seek times could really be reduced, like if you're using an SSD, then this will really kind of promote the use of secondary indexes. Secondary indexes would become less problematic in that case. But secondary indexes over range queries could be problematic. All right. Now we just talk about conjunction. I alluded to this before. So we have a set of conditions that are all conjoined. And so what you have to do there is you just basically have to say, well, if I'm going to have these conditions, if I have an index, so let's say I have an index. If there's no index on anything, we just have to do a table scan, right? But let's say there's an index on, the first condition, the first data condition here on the select, there's an index for that, and the second one there isn't. So it's something like saying we want the name. Let's say we have an index on name, and then we have something about the student's number of credits, and we don't have an index on that. So you want to just evaluate, you want to use the indexes where you can, and then once you've kind of whittled it down using the index, then you want to apply the rest of the conditions on whatever that return set is. So you have to make a choice then as to which of these are you going to use the index for, okay, to get the fastest speed. And whatever is the most discriminative is the one you want to use. So remember I had that example where I was talking about salary and department. You'd want to use the salary one if it's an exact value of a salary, because that's much more discriminative than the department, right? So that will whittle it down here much quicker to a smaller set, and then you can apply you can hand apply the conditions on what's in that set. All right, so that's kind of the way you deal with conjunction. You could also remember, though, that you might actually have a B+ tree that has been built on that exact conjunction. So you might have actually have a B+ tree that is built on that conjunction. In that case, you probably want to just use that, right? Because that'll, I mean, it was built for that, and so why not use that? So that might be another strategy. So there might be a choice here. Disjunction, how much you can do about disjunction? You just have to kind of, you're going to have to kind of. I mean, it's tough. It's probably going to require a table scan. I mean, when you have disjunction, right? Because I mean, let's see, is it going to always require a table scan? Well, you could potentially have it break it up and do one with an index and then another one with an index. Yeah, you could do that. That's a strategy where you use an indexes and then you have these sets and then you just conjoin the sets. But anyways, disjunction is usually pretty tough. All right, so that covers selection. So that covers how we basically use indexes when we do selection. Okay, now we're going to look at projection. So projection, there's little really that you can do with projection. So each record has to get processed in turn, and then you're going to just basically discard the unused attribute. So you're going to slim it down. So if you need to remove duplicates, so if you say select distinct persona number, then the system should be smart enough to know that, well, they're distinct by definition, or select distinct over something declared to be unique. Well, yeah, okay, it's going to be unique anyway. So, but if it isn't, right, then like for instance, the name, like select distinct name, then you're going to have to kind of keep something around, and it's going to potentially be growing in memory. That is the way you do is you have a giant hash table, and you just stuff as things come by, right? As you're getting as values are coming by in the projection, you add them to that hash, and before you report them, before you say this is a projection value, you check to see if it's already in the hash, and if it's already in the hash, you just ignore it, right? So that's how you remove duplicates, just with a hash table. Notice this can get a little complicated if that hash. So the hash table is now with remove duplicates. We'll get to this when we talk about execution, but the thing is that you guys are all familiar with iterators, I hope, in programming languages. So these things kind of form the same kind of structure as an iterator. That is that you might have the projection. What it does is that it's getting something from below, and a big table from below is getting fed into it. Just assume that the projection operator basically is implemented as an iterator. So it just looks and it says, okay, fine, I'll send you back up. I'll send you up. It looks at one and says, I'll send you up. And then the next one comes along and it says, okay, are you already in the hash? Okay, well, you're not, so I'll send you up. And it kind of does that. But as it does this, the hash is getting bigger and bigger, okay? And so the database algorithms traditionally have to be implemented so that if that hash gets so big that it doesn't fit in main memory, the system still has to work. So databases are by definition something that should work under kind of low memory requirements. Whether they do that anymore, I'm not sure. But anyways, the point is that you have something, when you have a distinct, it's incurring extra memory. You have to keep around memory during the processing. So that's a cost, and you do the check with the. And there's a cost. I mean, it's not that much cost in terms of computing and checking a hash and inserting into a hash, but the memory could potentially get big. All right. But anyways, there's not much else you can do of anything special. All right, so you're on the fly. This is what I was just saying. Removal of duplicates by hand. Okay, so now we look at joins. Okay, so here's where indexes better come to the rescue. All right, so if we basically say the following, that I mean, a nested loop join. This is a bad join. You don't want to do this join. I mean, no one implements this join. This is the kind of join that maybe would be implemented. This is a very, very naive implementation of the join. Basically what it does, it just brute forces it. So what we're doing here is we're joining. We have R1 and we have A, and we have R2 and we have A. All right, we have n sub 1 tuples on in R1 and some 2 tuples in R2. So basically what we do, the strategy here is that what you do is you just go to the first tuple of R1, and then you've got to say, does it join with the first tuple of R2? Does it join with the second tuple of R2? Does it? And then you go, you get the idea. You're going to be computing every single possible combination. All right. Well, that's not. That's going to require an insane number of disk seeks. So one number of tuples in the first table times the number of tuples in the second table disk seek. So that doesn't make any sense at all. So this one here is the kind of your standard implementation. So what you do is you do a block-oriented version of that. So in the block-oriented version of it, you snap up a whole block of values of we snap up a block of relation 1, and then you go through all the values in that. Well, you go through the values in that, and you simultaneously look at all the blocks in relation 2, and you compute the join. All right. So it's it's like, well, every time you find a join, you just add it to so join is also one of those things where it's like an iterator. So I have 2 tables, and every time I find a join, I'll just say, boom. If anything was, I'll say, here's the result. And if anybody was asking as an iteration, somebody was calling me as an iterator, I pass it up so they can now see it. All right. So they're getting it. So basically what I do is I go through this thing, I take a block of R1, and I take a block of R2. I see, well, do I get a join here anywhere? Well, every time I find a join, I'll just toss it up to whoever's calling me. And then I'll go through all the blocks of R2, checking for joins. And then once all that's done, then I'll go up to the next block in R1. So it's just like it's still that kind of all combinations kind of naive join, but it's at least doing it by blocks. All right. So the total number of disk seeks are going to be the number of tuples divided by the blocking factor of this relation R1, and then the number of tuples in R2 divided by the blocking factor of R2. So that'll give you, so like, if you can hit like 20 records per block, then it's going to give you quite a bit of speed up that way. All right. I mean, okay. So technically speaking, you want to do like a floor or something, or a ceiling. But anyways, a ceiling. All right. Yeah, so that's that. All right. So, but the thing is that what we want, of course, and it's quite natural to have this. So that is, we want to have at least an index on one or both sides of the join. Okay. So in this case here, we might have something like this, where we have this might be something where we have like R1 has a foreign key to R2. That's probably what this is going to represent. And R2 has a primary index on A. Okay, but it's a foreign key going out of that actually can't be right here, because if you look at it, that's at least in this example here, that's not true, because the there's repeats of the so they're not primary keys there. But I should fix that actually to make it kind of more realistic, because typically what you're talking about here is you're talking about like a join of foreign to primary key, which is so foreign key joins. This is going to happen all the time. So I wish I should have actually made it so that change these so I could allow duplicates here, but these would just be single. Anyways, so anyways, an index exists on the join attributes of R2 here. So but it doesn't exist on R1. So what are you going to do then? You're going to process in a block fashion. You're going to by block, you're going to go through all the tuples in as you're calculating the join between R1 and R2. You're going to the natural join. You're going to go through block by block here, and then every time you come to something here, you're going to basically, to see if it's here, you're going to do a index search. All right. So what that's going to give you then is it's going to give you, all right, so we have N1 here, the number of tuples there, and we have N2, the number of tuples there. What that's going to give you, it's going to give you log base big of N2 time to do each of these searches here. So N1, number of tuples in 1, probably divided by the blocks, if you want to talk about seeks or something, times log base big of N2. All right. And when I say log base big, I mean, I'm talking about log base, probably something like log base. I mean, if you think, those internal nodes in B plus trees they're just search key values and pointers. So you can stuff probably hundreds and maybe more than 100. Let's say there's log base 100. Log base 100 that squashes big numbers down pretty quickly, right? It could be even higher than that. So, anyways, it almost feels constant there. So you get really good improvement there just with one simple index. All right, so then you have a case here where it's even better, where you could even do better. You can basically, so this right here is still multiplying by something. In a merge join, when you get a merge join going, what the merge join does is it says that we have keys. We have indexes. Well, a merge join is very okay. So when we have these are basically in we have primary keys on both A. We have primary key indexes on both A in this table and that table. So all you do is simply just keep pointers on. You just walk through both the files. So you just go through the N1 tuples here and the N2 tuples here in order. And since they're already going to be in sorted order, as you find matches, you join them. So it's really easy. So you just kind of zip things up. So it's like they're both in order, and then you just kind of join them together like that. So it's just really simple. That's why it's called a merge join. Hybrid merge join is that you have a primary on one and a secondary on another. It's essentially going to give you major speed up as well. So these are the ordered. They're ordered here. They're going to be ordered on A. Here, there's a secondary index on A, and yeah. So anyways, it's and then the double merge join is where you have secondary indexes on both, and so I mean these are just kind of a little bit worse performing. I'm not sure how often this will come up, but well, actually, this will come up quite a bit if you think about it. A secondary index on both. So if you're merging on some kind of attribute where the attribute is it's not certainly not a clustering attribute, so you build a secondary index on it in both tables, but you want to do a join across both those tables, then you're going to be getting this kind of strategy here. Let's see what more to say about this. Okay. All right. So when we have a join where we don't have any indexes, so that was like this this guy right here. All right. So there's no indexes built. It's not using any indexes. And unfortunately, that happens, right? You have joins where you're not going to have indexes. You can do it this way. You can do it as a loop, nested loop join, but there's another way of doing it, and that is to do it as a hash join. So here's how hash joins work. So the hash join, so we don't have any indices, and so these are widely used. I believe PostgreSQL we use hash joins all over the place. One second, I just got to check. All right. So here's how it works. Basically, for the hash join, for each relation, the values for the join attributes are hashed into buckets. Okay. So what you're going to do then is you're going to basically go through all the attributes here, and you're going to hash them into buckets. And you're going to have for each bucket you're going to have like a kind of a corresponding bucket over here. So what you're going to do is you're going to go through all the values in both of the tables, and you're just going to kind of on the fly. So you're going to walk through. That's one tuples. You're going to walk through all these. I mean, the number of blocks is a different story. I mean, you're going to not access that many blocks to do this. But what you're going to wind up doing is you're going to wind up basically, you're going to have like a set of buckets. Let's say we have 10 buckets, right? Or in this case, we just have 3 buckets. Each of these values here are going to wind up just randomly hashing it into one of the buckets. So this will actually hash into this bucket. C will hash into that bucket. A will hash into that bucket. G will hash into that bucket. E will hash into that bucket. Okay, just kind of randomly based on the hash function. Right, using the same hash function, D over here is going to hash into that bucket, But here's the important point. A is going to hash into the same bucket here, the corresponding bucket, right? Because we're using the same hash function. So if these are just basically, you run the hash function on A here, and it determines, okay, well, based on the bits, it's going to say this, you go into that bucket. You go into the first bucket in my list. Well, over here, when it comes to A and it does the hash, it'll basically say, okay, based on the bits, you go into the first bucket in my list. And then, so that in both cases, it winds up in the same bucket. All right. So you go through both relations and you just kind of generate these hash buckets. Now what you do is you just go and you say, well, all the joins then are going to be the you're going to look at corresponding hash buckets at the same time. So when I look at this corresponding hash bucket, and then there's back pointers to saying which tuple it was and all that. So when I look at this right here, I say, oh, well, A, he's in there, and he matches here. So let's say there's a back pointer to that tuple, and there's a back pointer to that tuple. Therefore, I am going to include in my answer this tuple joined with that tuple. Oh, there's another one. I'm going to take this tuple joined with that tuple. So, and then I'm going to look and say, okay, G, no. Okay, so now I'm done, right? So I might have some indexes in here that are going to help me do this, but let's just say I can just do it in some kind of sort order. So in other words, I can do it in some kind of, when I say here, I have this A in this hash bucket here, I can have an easy way of finding the A over here. I don't have to, do a sequential search every time, but whatever. It's just kind of implementation detail, actually. Anyways, by doing that, I find all the joins on A, right? And then I go to the next corresponding pair of hash buckets, and I do the same thing, right? So this is a way that you're going to compute the join. If you think about it, it works, right? So this is widely used. So this is going to be, if you think about it, this is most likely going to have better properties. It's going to be a little bit more memory intensive to keep things around, but it's going to have better properties than going through and just grinding through on a nested block-oriented nested join, most likely. Okay, so that was. I just wanted you guys to see that when you don't have any indexes, you are typically going to resort to one of these hash joins. All right, so that kind of covers joins. Now let's talk a little bit about set operators. Okay, set operators, we have union, intersect, and difference. Okay, for intersect and difference, records with identical key values must be found in order to eliminate tuples. So intersection and difference. For union, it's fine, but if you have to remove okay. So in short, intersect and differences as well as union with duplicates removed are going to require us to remove to find records with identical key values in each of the two sets. Okay, so to do this, we're going to again use a kind of a hashing, the same kind of thing we use as a hash join, same kind of strategy. So suppose that we have a set operation on R1 and R2. All right, so we have set R1 and set R2. So both have kind of they've generated sets. Okay, so the first step then is, but R1, let's say it's R1 minus R2. So we can report any R1 that is not in R2, all right? But if it's in R2, then it's got to get removed, all right? It's got to be taken away. So the first step is, in each case, is to construct a matching sets of hash buckets, just like we did with the hash join. So we take, well, say, okay, we're going to take 10 buckets, and then we're going to take all the elements in elements in R1, and we're going to hash them into their proper bucket, and then we're going to take all the elements of R2 and we're going to hash them into their corresponding proper bucket. All right, and then all we do is we just go through and we bring. Okay, so this is again a case where it's like these could get really, really big. So let's assume it doesn't fit in main memory, but we bring R1 for up to K, we have 10 buckets, whatever. Okay, so the first one, we're going to basically bring in the first R1's bucket, number 1, and R2's bucket, number 1. Okay, so they're both brought into main memory, right? And then all we do is basically this. For set intersection, we just, for each tuple in R2, probe the index of R1 and delete it from R1 if no match is found. Okay. For each tuple in R2, probe the index of R1. All right, so, and delete the tuple from R1 if no match is found. For each tuple, I believe for each tuple in R1 here. This should be R1I. So I find that, then probe the index of R2. If it's there, I'm sorry, but it was right the way it was. So I'll have to kind of think. I think there's something kind of weird going on here, because what we're going to turn back here is the hash bucket, the corresponding hash bucket for R1. So in this case here, I believe with the intersection, we have to do the other side of the intersection. So if it's in R1, but it's not in R2. So for each tuple in R1 sub I instead, probe the index of R2 and delete the tuple from R1 if no match is found. That's right. Yeah, so that would be the fix. Or there's a typo here. Okay, for set difference, so R1, and R2 there. For each tuple in R2, probe the index for R1. So if it's there, so in other words, if they're going to be minusing out, then delete the tuple from R1. So that makes sense. So that means that, like, well, in my set I probe the hash. One particular hash bucket has the value E, and then I'm doing a set difference, but then I probe the other corresponding bucket for the second relation, and it has E in it for the particular pair that I'm looking at. Then I got to get rid of E in R1, and then I basically pass back the updated R1 as the answer. Right? So this is a way in which you do the you can do these kind of set operations. The thing to keep in mind here, just something to kind of just point out, is that this is a set difference is particularly bad because set difference cannot. It has to be doesn't have to be completely done. So what it can do is it can do one of these hash buckets. So once it's done with a particular hash bucket, then and only then it can start passing things back as, okay, this is going to make it through the set difference. Right? So, but I'm not really sure if PostgreSQL would do that. My experience with PostgreSQL isn't very smart about it, and it blocks completely on set difference, but it doesn't really have to if you think about it, this kind of hashing operation. Anyways, hopefully that'll make sense to you later. All right, aggregation. The hard part is basically just to compute the aggregate groups. So you're going to have to kind of compute these groups, and the key thing here is that when you compute the group, so basically department name, average salary, instructor, group by department name. Okay, so you're going to go through the whole table, and you're going to be doing a grouping operator, and you're going to define these groups. And as you're going through, you're going to be adding things. You're probably going to do it by hashing, and I mean, of course, all these things you do by hashing, you could do by sorting also, but hashing is, I think, a lot of times preferred. Anyways, so you're going to create these hash you're going to hash the groups, whatever the group values are. It's going to forming some kind of hash structure. And then the idea then is that as you add elements to that, if there's an aggregation function, you can be a little tricky. But like count, you don't have to. I mean, you can just basically compute the aggregates on the fly. All right, so counts are easy because every time you add something, you just kind of bump up the aggregate value. Averages are a little trickier, but you can still do it because you keep a sum total, and then you can just divide at the end. So you have to kind of keep two variables or something on an average. But anyways, computing the aggregates on the fly is going to be a big win because then you don't have to do it you don't have to kind of do this separate process. All right, so now we can finally talk a little bit about evaluation. Let's see, I hope we have the time here. So evaluation, yeah, so in a pipelined architecture, so basically we have, they're always going to be pipelines. So basically the tuples are going to flow from department up to the select here, and they're going to flow into the join, all right? And then from the join, they're going to flow up here. So if you're using iterators, that means the moment I have one department, and then, let's say I have 1 million departments here, but I take one of them, it is and meet Hussid, then already we're ready to kind of do a calculation of the join here. Of course, the join has to wait on the instructors to start piling up, but it might actually do might pass up an instructor here, and then it sees, oh, there's an instructor here that is actually in the same, that is in some department coming up from here, and then it's going to give the name. So it can already be producing a name here when it still hasn't consumed all the departments out here or instructors out here, right? So that's why it's called pipeline. So the lazy evaluation aspect of pipelining, which is the easy one to implement, that's kind of our iterator approach in Python or something like that, which you've got to wait. You basically create and supply tuples to the parents when they're requested. So when the iteration call is made from above, you process that. But in producer-driven, you might have buffers here. So this thing might actually be producing a buffer that this thing then sucks off that buffer, all right? And likewise, so you could make it so it was like multiprocessor, all right? So it's kind of like parallel. So the demand-driven is easier to implement. Producer is really going to be hard to implement. But the question is always like, which ones get blocked? So set difference will have a tendency to get blocked. So it can't really say anything up to whoever's kind of waiting on it in the pipeline. It has to wait for quite a while before it can pass stuff up. All right. So anyways, here we go. So anyways, this is what PostgreSQL really does. I think it's got something kind of sophisticated. It does a lot for parallel processing. So I'm sure it has a pretty complicated evaluation engine. It's not just a simple iterator. I'm sure it's got more going than that. But anyways, to find out what PostgreSQL is doing, so you're going to do this in recitation. You're going to be doing a lot of this actually. Explain. So there's explain and there's explain analyze. Explain analyze will actually run it and give you the actual values. Explain will just do a prediction. But if you look right here, you just kind of put explain analyze or explain in front of your query, and you'll get some kind of analysis. So there's a lot of stuff on the web that will tell you how to read these things. This cost right here is like the startup cost. How long does it take to get started with the operation? 0. You can start it immediately. And then how long is it going to take to finish it? All right. And then likewise, and then down here, what is it actually doing? It's doing a filter on salary greater than 70 and then computer science department. These units right here are just kind of make-believe units. So you can't really tie them to anything. It's just kind of it doesn't really correspond to anything. I don't know. There's probably some factor you can multiply by to get what real time would be, but these are kind of internal time units. All right. So yeah. So now if you look right here, so if we look at the intersect here, so remember we noticed that this was equivalent. Goes back to the beginning. This right here is actually equivalent to this right here. We're doing intersect of the two sets. But if you look at the query plan, PostgreSQL is not smart enough to figure it out. So, what it's doing here is it's doing a little bit more in terms of, it's doing sequential scans on instructor twice here. So this is how many rows it's getting out. Let's say this is explain. All right, so yeah, here's something involving a join. And so look right here, the join, it's doing a hash join here. So, yeah, so, to understand these, I mean, it's kind of working from the bottom out. So what it's doing here is it's basically going to go over, it's doing a sequential scan on department, where it's looking for the building is Watson building, and okay, so salary is Watson building is the building for the department, and then the salary, that's for the instructor. Yeah, so that's not going to be after the join. So sequential scan here on department. So if you had happened to have sequential scan, that means you're doing a table scan. So if you actually had built a index on the building of the departments, then you would see here most likely what it would do is it would be using the index to do it. There's one thing to keep in mind. I'm not really sure what PostgreSQL does, and is that, I mean, when you have really small databases, like this university database is really, really small. So sometimes what optimizers do is they just look and they think, well, what's the size of the table? And they see what the size of the table is. They just, like, the table is the size of like 12 tuples or something, or 40 tuples or something. Enough tuples just to fit into a block. That's the full size of the table. Sometimes a smart optimizer will just say, okay, ignore indexes, just ignore them, because it'd be much faster for me to ignore that stuff and just to grab it. All right. So you really have to have a larger database to actually get to make sure the indexing is kicking in. All right. And certainly for it to make any kind of noticeable difference, you need to have a fairly large database. The database, yeah, here's some more of that. Okay, so the database, just a kind of a quick thing about the database. I should say a little bit about recitation 2. I ran out of time, but let me just say a little bit about recitation 2. So in recitation 2, which I'm going to release today, again, let me repeat, please, please, please run this on your own PostgreSQL. I know some people want PostgreSQL for their projects because their projects are going to need to have a server running. But for this, you need to run it on your own, because if you do this over the departments, if you've got a department account, don't do this on the department's account. Anyways, I'm going to send you guys a script where you're going to create like a little dwarf galaxy. So you're going to create like, I think that like I created 10 million stars. All right. So you're going to create 10 million stars. And that means you're going to get like 400 million planets. And then you're going to have like wormholes that go through there. And then you're going to have some planets that have life, some planets that have civilization. Anyways, it's a big, big database. What's cool is that you can just generate it. So the code is going to let you generate it. So and then I'm going to say answer these queries. So when you answer these queries, it's kind of clear that you're going to have to get the actual answer states, you're going to have to build indexes. Otherwise, it's going to take forever. So this will force you into building indexes. So it's I think it's kind of a cool project, a cool recitation. And that will give you a lot of experience with kind of like doing explain, analyze, and kind of, working with big data. Because this will be, I mean, it's pretty big data. So I'm going to say that you build 10 million planets, but if you like bust down your machine when you try to build 10 million planets, then just build 1 million planets. On this little laptop here, I was able to build 10 million planets. I'm sorry, 10 million stars, and then like 400 million planets, which is actually pretty small when they go by dwarf galaxy measures. So it'd be really cool if somebody could just really go whole hog and like make, like a billion star example. That would be cool. But I don't think I could run that on mine. I think I would run out of disk space. So if anybody can run the billion case, that would be sweet. All right. All right. So are there any questions? I did that. Okay, somebody asked, do you recommend doing it on an SSD? I did it on an SSD. So I mean, because I don't have a moving disk on my laptop anymore. So yeah, I did it on an SSD. Yeah, I would recommend it, I guess. It'd be kind of cool to see what would happen if people did it on disk, but I'm just assuming everybody has SSD at this point. Are there any other questions? Okay then. Well, great. Oh, another question. That's a good question. How much space it was? That's actually not so easy to determine. You have to go to a directory. On in PostgreSQL and do ls it as it's doing. So it's because in PostgreSQL doesn't really tell you the name. You just see certain files getting bigger. I don't know exactly, but I think it was definitely over a gig. Definitely over a gig. I would say like roughly. We can do the calculation. Actually, it's not that hard. I mean, when you see the file, you'll be able to see it. But I would guess a couple gigs, maybe a gig and a half or something. It wasn't that much actually. But and it doesn't take that long. But I was pretty proud that I got it up to 10 million stars. So I can do it up to 10 million stars. I imagine you guys can do it up to 10 million stars. But if you can't, do it up to 1 million stars. But you need at least 1 million stars. So, but I'll share this with you soon, so you'll see.
Mr. Minuk,
Yeah.
if I want to see your lectures, the videos, where can I find them exactly on Cambro?
You have to go down into the content, or what was it? It's the contents or something, and then you click on that, and then you see lectures. It's like okay. I mean, I can put it on the front page. I promise I'll do that.
Okay.
I mean, I'll make a link. I was actually intending to do that. Lecture link. Okay. Well, there's some people who want to talk to me privately, so they can do that. But let me just stop the recording first, and then other people can kind of go. I'll keep this going here. So stop share. Let's see. 1 second. Stop share. Then stop record.